All right, let's continue with Note 6, Part 2. Here's our next example. In example 5, the following table represents an incomplete probability distribution of weekly air conditioning. With a discrete probability distribution, your X variable has to be numerical values, a finite number of them. Probabilities have to be numbers between 0 and 1, and they have to total 1. That actually helps us find this value. It has to be 0.27 for the total to be 1. Now, usually this is built in columns. I'm going to ask you really quick to pause the video and build a column for x times p of x, or actually a row, and then a row for x squared times p of x, and find those totals. And I'll do the same. I'll see you in a couple of seconds. Okay, let's continue. Now, remember, this table represents the probability distribution of weekly air conditioning units ordered. We filled in the table to make the probability row add up to 1. Now we're going to calculate the expected values. The expected value formula is the same formula as the mean. It's the sum of the column entitled x times p of x. Well, the sum of that column is 2.55. If we were to interpret that, we would say, on average, we are selling 2.5 air conditioning units every week. That's good. I mean, if we weren't selling any, or if we had a negative value there, of course, that would mean that we're not making any money. We're not really needing to keep any in stock. So important to know the average amount that we're selling weekly. Some weeks we may get back ordered. Some weeks we may sell more. But on average, it is a good business for us to have because we're selling 2.5 every week. All right, to find the standard deviation, we start off by finding the variance. The formula for the variance is the sum of the column entitled x squared times p of x. That is a number. From it, we subtract the mean squared. I don't know why I put it in parentheses. Let's take them off. Let's plug in. The sum of the column entitled x squared times p of x is at 8.03. Minus the mean that we just found, 2.55 squared. When I put it into my calculator, I do get 1.5275 is my variance, but they asked us for the standard deviation. So you'll take the square root of the variance, just like we have all semester, and we get 1.2359. All right. And the significance here is if your standard deviation is really small, like this one is, that means that the standard deviation points are clustered around the mean. Larger means that the data are more widely dispersed, but that is a good thing. Now, example number 6 on the next page, we will do in class together, but it's a really neat way to kind of work it backwards. We're actually going to look at insurance problems more in our upcoming, or actually in our homework, and we'll do a couple of those together. So I'll see you then. Now, the next type of distribution we're going to look at is called a binomial distribution. With a binomial distribution, we have to, again, have a fixed number of trials. Each trial can result in only 2 outcomes. Whatever the outcome we're looking at is determined to be our success. And of course, the opposite would be the failure. The key thing that I wanted to point out here is that a success is what we define it to be. It can be that you died in a plane crash. It can be that you have diabetes or blood pressure issues. A success is that you meet the description of the event we're trying to look at. It is not necessarily a positive thing. Okay, each trial is independent. Oops, that wasn't good. From all the other trials, and each trial has to have the same probability of a success. A really great example of that is our coin toss. Are there a fixed number of trials? Yes, we're going to toss the coin 3 times. Each trial can result in only 2 outcomes, a tail or a head. Now, it doesn't have to be 50-50. This one just happens to be that. Each trial is independent. Yes, every coin toss is independent. What happened on the first coin toss does not affect what's going to happen on the second, or on the third, or on the fourth. And each trial has the same probability of success. So yes, this is a good example of a binomial distribution. All right, the binomial distribution comes with a formula, and this is him. The X represents the number of successes, N is the number of trials, P is the probability of success, Q is the probability of a failure, and the probability of a success and a failure have to add up to 1. Now, they never, ever, ever tell you what the failure is. You find it yourself. Q can be found by taking 1 minus P. Now, we're going to look at the formula for the mean and variance of the binomial distribution, and then we'll go straight into some examples. All right, the mean for the binomial distribution is N times P, and the variance, we're going to have to add that, is N times P times Q. That is the formula for the variance. Oh, and I should have written it this way. There you go. Now, the standard deviation is still the square root of the variance, so that hasn't changed any. Now, let's just jump right in. All right, on this first example, it says a company produces fine crystal from experience that, a company that produces fine crystal knows from experience that 10% of its goblets have cosmetic flaws and must be classified as seconds. 10% is our P. They always give us P in the problem, whether it's in percent, fraction, or decimal, but the P is going to be provided for us. Now, 10% of the goblets have cosmetic flaws and are classified as seconds. So them being flawed is a success. So among 6 randomly selected goblets, that makes our N 6. How likely is it that only one is a second? So one of them is a second or a flawed goblet. That's our X, the number of successes that we're looking for. Let's use our formula to find this one. If I'm looking for the probability that exactly one has flaws and is classified as second, I'm going to take a combination of 6 things taken one at a time, times the probability of a success, which is 0.1, raised to the X power, times Q. Wait a minute, they didn't give us Q, but we know from the previous page that I can find Q by taking 1 minus P, and that in this case will be 0.9. Oops. And right here, instead of X, X is 1, and Q is raised to the N minus X power, which would be 5. This pair of exponents always have to add up to our N. Now, when you put that into the calculator, you'll put the combination in first, times 0.1 to the 1 power, times 0.9 to the 5th power. You should get 0.354. Now in class, we're going to look that same probability up in our table, and we're going to use the table for this second example. So get your binomial distribution table out. We're still working with 6 goblets. What is the probability that at least 2 are seconds? Now we have 6 goblets total. At least 2 of them would mean that the number of successes would be 2, 3, 4, 5, all the way up to 6. All of those are considered at least 2. Now, in class, we defined how, or decided and described how we know when we can use the table and when to use the formula. If your P is provided on the table, we're going to use the table. letter A up here was actually in the table, but I needed you to learn how to use the formula because it's required on some of the homework. So we always do that first. But on this one, I want you to look at your table. Go under n is equal to 6 and scoot over to x is 2 underneath a p of 0.1. So I'm going to find the probability of 2, the probability of 3, the probability of 4, the probability of 5, and the probability of 6 in my table. The probability of 2 is 0.098. Using my table, I'm going to find the probability of 3, 0.015. Probability of 4, 0.001. Probability of 5. Now at this point, it gets so small that the answer is almost 0, and they don't even show that one because it is also almost 0. We add them together. Our answer is 0.114. Remember, almost 0 and almost 1 are viable answers. We are going to omit part C. Now, on this next part, we're going to do it on the next video. We're going to set up just the X part because that's the interesting one. And also our table doesn't go up to 25. So we will, we'll just be setting up the X part. I'll see you in the next video.